Thank you, Wendelin, and it's an absolutely great honor and pleasure to be here, and thank you all for coming. So this is my title, these are my affiliations, and let's go on, but only one by one. So just as an appetizer, here you see the map of 3 cities with streets and avenues which are partly or totally made one way by the city council. Now, in the rightmost maps, in the city of the rightmost map, not right, is that rightmost? For you, it's leftmost map, there is sort of grassroots democracy. They ask the people in each single block to decide whether they want the streets being one way, clockwise or counterclockwise around the block. And if there is consensus between 2 blocks, as you see here, there is consensus. These guys want one way around counterclockwise. These guys want it clockwise, so there is consensus there. Then that street is made one way. If there is no consensus, then the street is not made one way, then it's just 2 ways. Now, you are a driver, and a sort of random driver. Whenever you arrive to a corner, you choose between the possibilities in the following way. If there is you choose a one-way street. You don't go against the traffic in one-way street. And you choose the one-way street with probability 1/2 and the non-one-way streets with probability 1/4, 1/4. For example, here you don't have, there is absolutely no one way from this corner going out. You choose 1/4, 1/4. If you arrive at this corner, it happens that you arrive at this corner, then you choose this direction with probability 1/2 and these 2 directions with probability 1/4, 1/4. It's clear, isn't it? A question is, this driver, how far this driver gets in long run? This is a huge city. How far it gets? Of course, if there was no one-way street at all, then we know what happens. But it's not very clear what happens here. Now, this second city is Manhattan. That's not totally democratically decided. Actually, the city council decides with coin flips whether to make the streets eastbound or westbound one way, and to make the avenues northbound or southbound one way. At each single corner, you can arrive with your car. You drive in this city now. You can arrive at each single corner from 2 different directions, and you can leave in 2 different directions. You decide by flipping a coin. Same question: how far you get in this city? How far in long run? How far you get in the long run? Right? Okay. When I ask how far, is it diffusive, sub-diffusive, super-diffusive? And here is a third example where a mathematical physicist is a mayor, and he knows about the 6-vertex model or the square ice model, and it's done in a truly sophisticated way. Some of you know what the 6-vertex model is. You would have the square lattice here, and you orient each single edge in one of the 2 possible ways, but with a constraint. And the constraint sounds like a mild one, but it's a very, very strict and confining one, that at each single corner you have 2 in, 2 out. Otherwise, uniform. And now the rules are the same. The driver starts, and at each single corner, flips a coin. You have 2 out, 2 in at each single corner, and you flip a coin to decide which direction to go. Now, these are the types of random walks I want to look at closer. And I tell you that these 3 examples will give 3 totally different answers. Right? The leftmost one will be diffusive. Central limit theorem with square root of time scale will hold. The Manhattan lattice, of course, by the way, you can easily imagine how to extend in higher dimensions. Then the story is not about cities, but about something else. But you can imagine how to do it in higher dimensions. The Manhattan will be super diffusive in 2 and 3 dimensions, and diffusive starting from 4 and up. And this one is not well understood yet, but the guess would be that in 2 dimensions it's super diffusive, and on the other hand, we know that in 3 or more it's diffusive. So these are the types of questions I want to ask. Sounds like a game, but it's more than that. And here is what I do, actually. start with I will define now my problem, start with a probability space with an ergodic ZD action on it. We all know what that means. By this script I only mean the possible steps of my random walker. I define on this probability space jump rates, not probabilities. I do things in continuous time because I want to allow a bit more general things. So jump rates, that means that for each single direction you have a non-negative and finite jump rate. And here you see the role of the random walk. Once you have omega sampled, small omega sampled from this space, a random walk is defined. That means a Markov process on the lattice ZD, which does the following. It's a Markovian, conditional on omega fixed, omega given it's Markovian, and if it happens that the random walker at time t is at site x, then it jumps to one of its neighbors with those rates I told you, but shifted by tau x, shifted to that point. So in other words, I have a translation invariant field of jump probabilities, random jump probabilities, which obey some rules, which I will tell you explicitly what they are. And I ask about this random walk, about the behavior. This is the general, what we call random walk in random environment. And just for notation, and it will be important later, that I separate the symmetric and anti-symmetric or skew-symmetric part of the jump rates, namely the rate along an edge, a directed edge, and against the same edge, but directed oppositely. So the average, that will be the symmetric part, and I note it by S, and the anti-symmetric part I note by V. And mind that this V, okay, I think I don't have a, yes. Okay, now my assumptions are the following. First of all, the jump rates are bistochastic. At each single lattice site, the sum of the rates of jumping away from that lattice site equals the sum of the rates jumping towards that lattice site from the neighbors. That's bistochasticity. And this adds up, this is equivalent to the fact that this is what I called V sub k, that those V sub k, if you lift them to the lattice, they define a flow on the lattice, which means a vector field on the lattice. And this condition is actually that vector field be divergence-free. Divergence-free vector field. I also assume that the jump rates are L2, are square integrable. So if it was random walks in discrete time, then these would be bounded. But I want to make it a bit more general. I allow faster rates, but with some constraint, namely that they be L2. But I also assume that there is a lower bound on the symmetric part of the jump rate. This is technical, it's called ellipticity, and it's a very important, it sounds like technical, but actually is deeply there, and unfortunately I can't get rid of that now. And there is a last condition which I call H-1, and don't try to understand this formula now. This formula is a sort of infrared bound on the Fourier transform of the covariances of the drifts. Take the drift field here and far away, these covariances take Fourier transform. You will see other disguises of this condition which are better understood. And these are my conditions. Now, why these conditions? So what are the first consequences of these conditions? First of all, if I travel with my random walker and I make a film of the environment as seen by the random walker, that's a natural thing to look at in this context, that will be a stationary and ergodic Markov process on the space omega. This follows from the bistochasticity. Actually, it's equivalent to the bistochasticity. So it has this type of consequence. The H-1 is it's deep thing. One of its consequences is that the random walk will not have an overall drift. Overall will be zero drift. So the random walk is not drifting away with a positive speed in some direction. And that's what I want to understand. How does it diffuse, not drift? From these two immediately, and the ergodic theorem immediately follows that I have a law of large numbers, strong law of large numbers for the displacement. I also have, now this last line here is a more sophisticated thing, but those in this field know it well, that from these conditions, lower and upper bound for the diffusivity follows. So I know that if I have these conditions, that I have a lower bound on the diffusivity and upper bound on the diffusivity, the central limit theorem question remains open. Is it true that the limit is Gaussian, which is a deep question? And here is a slide for those of you who prefer continuous space and diffusions. Take, if you want it that way, take a diffusion generator which looks like this. This is a symmetric part where A is a symmetric positive definite matrix valued random field which is translation invariant. V is an almost surely divergence field drift field which is ergodic and translation invariant, and this is the diffusion I look at, and that's exactly the same type of problem. Now, one of the physical motivations, just to go beyond just this game with the cities and all that, is that actually this is a mathematical model, not a derived model, but a good analog for the diffusion of particles suspended in turbulent flow. Incompressible turbulent flow. The divergence-free means incompressibility. So it's physically motivated. And the history goes back, okay, in a sense, to Lucretius Carus, which, to the Rerum Naturae. I will show you a quote from the second book of the Rerum Naturae, where Lucretius Carus describes in very nice poetic terms exactly this phenomenon, which we all know, that if you look in a sunbeam, these dust, how the dust moves in a random way. And of course, that's not mathematics, but mathematically it started, the mathematical story started in the late 70s, early 80s with Kozlov and Papanikolaou and Varadan. You will see more from the history. And here is the quote from Lucretius Carus, which I love. And if you read these lines, the English translation, those objects also move, which we can mark in some beams, though it not appears what blows do urge them. So that's what I... Okay, here is a proposition which goes, but this is in a sense 19th century mathematics, Helmholtz's theorem. We all know from what we learned in say, introductory electrodynamics, that if you have a divergence-free vector field in R3 with some conditions, you can find another vector field, which in physics is called the vector potential, to which this divergence-free vector field will be the curl. Now, this is more general than just this particular statement. Don't read the details. What is written there is the following: given on the lattice a divergence-free vector field, as I define my V, there exists an object which I call a tensor field, and on the lattice, which is stationary increments, is a co-cycle, and to which my original vector field is, in a sense, a curl. So this is what you see on the first line. But mind, H will be of stationary increments, not stationary. Because V is a sort of derivative, and that was stationary with respect to translations, right? So this is a theorem, and the H-1 condition is equivalent to saying that this stream tensor, which you call a stream tensor, this stream tensor is actually not stationary increment, but stationary. It's a special case. Now, those of you, and many of you know well what this means in 2 dimensions. In 2 dimensions, this H would be the height function. In 2 dimensions, this reduces to the fact if on the 2-dimensional lattice you have a divergence-free vector field, then there exists a height function to which this vector field will be the 2-dimensional curl. And the question is whether this height function is stationary increment like the Gaussian free field, or stationary like in 3 dimensions the Gaussian free field, right? Okay, so this is an adaptation of Helmholtz's theorem, and here is a result, actually 2 results, which I put in one single theorem, but these are 2 papers actually, which are the main theorems about, main theorems I'm involved in this context. Namely, one is a joint paper with Gadi Cosma, which is just out in the Annals of Probability, which says that under the conditions I stated, okay, let's say the central limit theorem holds for the displacement in the annealed setup. That means in probability, there are two sources of probability, namely the random environment is random, and given the environment, the walk is random. But given the environment, so you have two sources of randomness. Now, what in the first theorem is stated is essentially, okay, it's technically a bit more, but what I state in the first statement is that taking both randomness in account, the central limit theorem holds. And in the second line, that's another paper, I make slightly stronger assumptions. Oh, sorry. I make slightly stronger assumptions. These assumptions, the h minus 1 amounts to S I actually assumed as being L2, but Helmholtz's second part of the Helmholtz theorem says that h is L2 is equivalent to h minus 1. Right? Now what I assume here is that h and S be slightly more integrable than just L2. I need a little bit more. If that holds, then the almost sure, that means the quenched central limit theorem holds. So that for typical environments, the central limit theorem for the displacement. If you go back to my original examples, the first example belongs to this one, is covered. I mean, in any dimension. The second example, the Manhattan, in 4 and more dimensions will be covered by this theorem. And the other one, which is the more subtle and most difficult, is the 6-vertex type. I don't know. I have a guess what happens in 2 dimensions, but in 3 and more dimensions is covered by this one. Now, here is some hints to history. Of course, as I told you, the mathematical story started in the late 70s with Sergei Kozlov and Papanikolaou and Varadan, and there are many, many works. This is a physically relevant question. That's why there are so many papers. There are overlaps and so on. The last strong result is in this paper by Claudio Landim, this book, that's a book by Claudio Landim, by Komorowski, Landim, and Olla, where they prove Yes, when they prove the theorem, but under the condition that H be in LD. So the gain is that, and S in L infinity. Now the gain is that I have it S and H in L2, or L2 plus epsilon for the quenched result. Good, and here are some elements of the proof. As my time is really running fast, I have to speed up. So the proof goes through proving, I speak of the proof of the quenched result, the second one. A quenched tightness, which says the following, and this goes back to one of the most beautiful papers from the 50s I read in my mathematical career, this of John Nash about, it was mentioned in one of the plenary lectures yesterday, about regularity of elliptic problems, parabolic and elliptic problems. Anyway, so what I do here, I take Nash's ideas, but extend from L infinity, from conditions to S and H being in L infinity to S and H being in L2 plus epsilon. But of course, ergodicity, so Nash does it deterministically. I do it using ergodicity and some randomness. But anyway, so there is an extension there. The second step is finding harmonic coordinates. Harmonic coordinates goes back, I tell you what the harmonic coordinates are. The displacement of the random walker is not a martingale. But maybe you can find some corrector, add something to the true place, the displacement, some other function, which should have satisfied some conditions, and the two together, the sum of the two might be a martingale. But if you do that, then you can apply the martingale central limit theorem, but you have to control the error you committed, so that will be another step, right? Now, finding the harmonic coordinates, if the idea of harmonic coordinates goes back to Sergei Kozlov and Osada's, a paper of Osada back in 1983, I think. But again, the point is that what's done there is valid for S and H in L infinity, and there is much work to do to go up to S and H. Actually, this holds for L2. I need L2 plus epsilon only at a step which is in this step. Good. Now this is solving an equation in Hilbert space. I don't have a chance to explain this equation. Solving an equation in Hilbert space that I'll show you what formally that means. Formally it means to prove about an operator. I just hint at this. So you have the infinitesimal generator, L be the infinitesimal generator of this environment process as seen from the random walker. It's not self-adjoint. My problem is always that I want to understand non-self-adjoint cases, right? So it has a self-adjoint and a non-self. You see L minus L star is a skew self-adjoint part. A sort of Laplacian acting on that Hilbert space is the self-adjoint part, and sandwich the non-self-adjoint into the inverse 1 over square root of the self-adjoint part. That's a positive definite. Okay, okay. Now, this doesn't make sense because you don't have a gap in the spectrum. So making sense of this operator as a well-defined skew self-adjoint operator is difficult. And that's the main technical element in proving that the previous equation does have a solution and actually has a unique solution. Then we applied the central limit, the martingale central limit theorem, and control the error. So this will be the field to which the solution of the previous equation is a gradient. But I want the central limit theorem for x, not for this change stuff. So I have to prove that the error is small. Now, here there is again a trick, namely, I need something more than just the usual ergodic theorem. I need something what is called the unrestricted. In higher dimension, there are tricky things here, and I need something more. Okay, so that's the idea of the proof. And let me just, I have one slide about what happens when h minus 1 doesn't hold. When this height function, for those who know well this two-dimensional story, when the height function is not stationary L2, but like the Gaussian free field, the two-dimensional Gaussian free field, right? Then you don't expect, you expect super-diffusivity. You expect super-diffusivity, and here is a theorem which I like it. Joint with Benedek Walko, joint with Benedek Walko. This is in continuum, not in the lattice. And it's easy to explain. Take the two-dimensional Gaussian free field, continuous Gaussian free field, pinned down at 0. It makes sense as a distribution, right? Now, I take my favorite local regularizing function, e to the minus x squared, just to make it smooth, and convolve it. Then I get a Gaussian field, which from far away looks like a Gaussian free field. From close, it doesn't look because it's smooth. But it has this sort of logarithmic increase and so on. And now I define a diffusion which does the following. The drift will be the two-dimensional curl of this smooth Gaussian free field. If I don't have noise, then this motion will just go round on the level lines of this smooth version of Gaussian free field, right? I add a little noise, no matter how small, but a little noise added. And what I expect, you see what I expect actually to happen, but what we are able to prove is super-diffusive lower bound. It's only log t instead of a power of log, what we can prove. But nevertheless, it's there, so its super-diffusivity is proved. And this is the prototype. This is not, okay, this is the prototype. On the lattice, it's more difficult. That's why we can't do the 6-vertex problem. And there are some other results which I don't go into detail now. So when h minus 1 fails, then super-diffusivity holds, and other methods should be applied. And here is my other type. Now I finished with the random walking random environment, and I go to another type of random motion with long memory. Namely, so forget about random walk in random environment. This will be a random walk in a sense in dynamical random environment. So the environment is changing in time, but due to the motion of the random walker in some natural way. There are some blah blah here, and with some formulas. The essential thing is the following. I'm curious about the long time behavior of random motions which do the following. They have some random element in it, some Brownian motion drives it, but prefers to not visit those regions which are highly visited in the past. It's pushed away by its own local time. So locally, for example, the lattice version locally does the following. L is its local time, the time spent up to time t, the time spent at site x. And the jump rate from x to a neighbor is proportional to an increasing function of the negative gradient of the local time. So if you have 4 neighbors, then you prefer to jump to the one where you spent less time in the past. But it depends on the gradient of the local time. And here is a continuous time and continuous space version, so diffusion version. So it's a diffusion on RD. This L is the occupation time measure of the diffusion. I give some initial value, but forget about that. It's essentially the occupation time measure, which is a random measure. And the diffusion is drifted by the negative gradient of its local time or occupation time measure, but it doesn't make sense to take the gradient of the occupation time, it's too singular. Smooth it out, convolve it with your favorite approximate delta. But with the condition that this approximate delta has positive Fourier transform. It's very important that it has positive Fourier transform. It will be important later. It's clear, so it's Brownian motion, but pushed away from where it spent long time. There is a long history, so this is a very interesting story because it started in physics in the early 80s, and it popped up the same or very similar problems popped up in the probability literature about 5 years later. These people in probability didn't know about the physics papers. So just the same, because it's a natural problem, that's why it popped up, but with no contact between the two groups. And here are some conjectures taken from the physics papers. Of course, the physics papers don't call these conjectures, they call them facts, but these are actual conjectures. Namely that this type of behavior in one dimension, this type of motion in one dimension should behave strongly super-diffusively, namely with a scaling order of time to the 2/3 rather than square root of time. In 2 dimensions, it should still be super-diffusive, but just marginally, with a logarithmic correction. And in 3 dimensions, it should be diffusive with central limit theorem holding. So these are if you go back to the papers in the 80s, physics paper of the 80s, and you translate into mathematical terms what you read there, this is what you conclude as conjectures. Here are and now some results. Okay, the results go back to the 90s, mid-90s. I started to work on these things in 1994, I think, and I was able to prove this time to the 2/3 scaling limit theorem for this type of a particular example, so not a general, lattice example with discrete time and some particular combinatorial facts about that random walk were used. But the guess is that this is universal, so I will come back to this. Then I met a young mathematician he's chairing now this session, and we were able to construct the scaling limit, not the convergence to the scaling limit, but the scaling limit process, which we published in a paper. And actually what I want to mention that in that paper with Wendelin, we also have this object, which today is called the Brownian web constructed. We didn't call it that name. Later it got this name, and then many papers were written about that. But actually what we constructed, this process, was through a construction which today is called the Brownian web. Anyway, so there are some partial results, and there is a robust, when I say robust, I mean a proof which does not rely on combinatorial details, analytic proof. Because these results are expected to be universal. These behaviors are expected to be, so if I describe the physics, local or the microscopic physics, then the global behavior should be universal. That's a great problem, whether it is or not, or open problem. But at least we were able to prove some super-diffusive bounds in a robust way. That means that without relying on microscopic details, only analytic proof. But what we can prove so the upper and lower bound, the upper bound is almost trivial, comes from an h-1 type of argument. and the lower bound is the non-trivial one, but it doesn't match. And actually what we expect here is that this be of order 4/3. We are not far from. So what is fully missing, is, for example, a fully robust proof by this, I told you what I mean, of this type of scaling behavior in 1D. This is indeed. I'm not sure I can go on. No. Doesn't move. I'm sorry. Can you help me? Maybe you can page. You should stop the clock. Does it go backwards? No, it doesn't go either way. No, but you see the beam, the laser works. Yes, I don't mind if you. I will always make some signal if I. Okay, so please turn the page. Okay, but not like this. Okay, but yes. Okay, in 2D, so these are now results. You think you can do something? Come on, no. No. Come back. Go back to the previous page. That's it. Now, in 2 dimensions, the same, okay, these are results, but I will tell you the exact conditions later. So these are not formulated now as theorems, but this type of results we. Yeah, these type of results are there. Namely, in 2 dimensions, indeed, we were able to prove with Benedek-Walko the super-diffusive. Thank you. Does it work now? Yeah, thanks. Super-diffusive lower bounds, far from what, okay, we expect here logarithmic correction. So t times some power of log t, we are able to prove lower bound of order log t, t times log t. Still, it's super-diffusive. And indeed, in 3 and more dimensions, with at that time PhD students of mine, we were able to prove to establish indeed the central limit theorems, diffusive scalings and central limit theorems in 3 and more dimensions. Let me make here a comment that people think that when the central limit theorem holds, that's just boring stuff because we know the central limit theorem from de Moivre and nothing new. It's not the case. So the phenomenon is there, and when you don't have independence, when the dependencies are not created by mathematicians, but by physics, then it's difficult to prove it. Right. I meant that there are theorems about mixing and all that, but those simply can't be applied in real problems. And here are some elements of the proof, maybe. Again, what I do, or what's the most natural thing to do, I will speak about the continuous, the diffusion case, because that's easier to speak about. To define a process, so okay, we have a non-Markovian process in d dimensions, finite dimensions, say 3 dimensions or 2 dimensions, which is terribly difficult because it has very non-trivial dependencies. We trade it for a Markov process in infinite dimension and try to do something this way. Namely, I define the environment as seen from the random walker, but what will be now the environment will be this gradient of the local time, but from the position of the random walker. It changes due to 2 things, namely that the random walker moves, so there is a shift, but the local time changes because it's local time, it's occupation time measure. Locally, it changes. So due to these two things, this Markov process moves like that. It will be a Markov process in an infinite-dimensional vector space. So for the function analyst, just to see something like that. So it's say, infinitely differentiable vector fields, which are gradients. And there are some very natural semi-norms defined here, which should be finite, and that defines metric and all that. So it's a nice object. The semi-norms say just that all partials increase slower than any power as you go far. And what happens here is, I still think it's a sort of miracle that this Markov process, which is a terribly complicated object, so you move, you create local time, but you move according to some law, that this has a very beautiful stationary measure. Namely, the stationary measure of this Markov process will be what I call here, it's a Gaussian, so on this field, on this function space, a Gaussian measure with zero mean, and covariance is what you see here, namely take the Green's function in the dimension where you are. So this is the Green's function, Laplacian Green's function. Convolve it with that smoothing object. Now this will not be covariance yet. And take the second derivative. So this will be a matrix, this is a vector field, so this will define the covariance structure. So actually, for those of you who know Gaussian free field, what you see here is essentially the gradient of Gaussian free field, smoothed. So regularized, locally regularized Gaussian free field. And that will be the stationary measure, ergodic and stationary measure of this. There are two proofs. Once you guess, it's not difficult, not so difficult to prove. There is one with Ito calculus, the other functional analytic proof, but it's a very interesting. So there is such a balance between drifting and building local time, which creates this. But no, don't think that it makes, the process is not Gaussian. At fixed time, it is Gaussian, but at different times are not jointly Gaussian, as it's usually in this type of stochastic partial differential equation type of things. And here is a theorem. All theorems hold, and here are the theorems. All theorems hold in the stationary regime. So I start with the local time, or the gradient of local time, initialized according to this measure. That's why I had at the beginning, when I defined the local time, I had some object there, an initialization value, because I can state my theorems only in the stationary regime. And the theorem is what you expect after I showed you without proper formulation, that in 3 and more dimensions, the finite dimensional distributions converge to those of a non-degenerate Wiener process. So that is central limit theorem, essentially, or invariance principle, less tightness of the process. And in 1 dimension, this is that paper with Pierre Tarrés and Benedek Valco, we have the super-diffusive bounds, lower and upper. And in 2 dimensions, again, we have the critical super-diffusive bounds. And we have some other results in this order, which I'm not going to show here. Now, here are some elements of the proof, which are very natural things, actually. Again, the trick is I have the displacement process, and the displacement process should be decomposed to a martingale and a corrector. So, it's not a martingale. What makes it a GAR, you have to subtract at any moment the conditional velocity, which is computable. And this corrector you see here is actually the integral. So other way said, if I subtract from the displacement this integral, then I get a martingale. And what you have to subtract will be an integral of a functional of this Markov process along the trajectory. Yeah, I have a stationary and ergodic Markov process in this infinite dimensional space. I have a functional of this which has a very special and simple looking form there, namely evaluate the function omega, the vector field omega at the origin. And integrate that one along the trajectory of the Markov process. And as we know about the martingale, we know everything. You have to, this is the point, this is the difficult part. This is the difficult part. Now in 3 and more dimensions, we want to prove central limit theorem. And what is done is extension of Kipnis-Varadhan theory to non-self-adjoint case, there are extensions. Before me, there were some extensions. Many extensions, not some, many, and important extensions. But this is another, okay, this is some sort of turbo version. And in 2 dimensions, and in 1 and 2 dimension, 1 doesn't appear here. I don't know why I didn't say 1 and 2. When I want to prove the super-diffusivity, actually what I proved that this object is super-diffusive. So this extracted value is superlinear. And what's done here is a resolvent method, which was, okay, it's right here initiated by, in this paper, it's not only this paper. In those years, there were a number of papers where, but the ideas go back to Varadar and to Yao, actually. And just to see what happens, always in these cases, when you want to understand this sort of functionals, additive functionals of ergodic Markov processes, you have to go to the Hilbert space of your omega with the measure, with the measure which is the station measure for the Markov process. And what happens here is, due to the fact that this is a Gaussian measure, you will get a very natural grading of your Hilbert space, which in different communities call different names. In physics, I learned it as Fock space, but probably most of you learned it as Wiener chaos, and that's the same thing. So decomposing to a Gaussian Hilbert space like that. And what happens is that the infinitesimal generator of this Markov process gets a particularly nice form. A particularly nice form, this will be, looks like a Laplacian, and it is a Laplacian, but not acting on RD, but acting on this Hilbert space by shifting functions, and some gradients acting on the Hilbert space, and some creation and annihilation operators well-defined. Now again, in Fock space context, you call it creation and annihilation operators. I don't know in Malavin calculus how they call it, but anyway. And proving that the infinitesimal generator has this form, that takes some time. So you need some tricky things, and the particular structure of the Gaussian Hilbert space and some elements of Malavin calculus are used here. Anyway, so I have a nice Gaussian Hilbert space. I have some very explicit operators acting on that Hilbert space, and what I have to do is to apply what I know, or to extend what I know to be applicable into this context. And actually what is done is a sector condition, but extended, so not quite taken for free from Setruman, Varadar, and Yao, but do something with it. Let me not go into technical details. And on the other hand, take this. So that's how we prove the central limit theorem, the diffusive behavior in 3 and more dimensions, and the super diffusive behavior in 1 and 2 dimensions. Only 2 is mentioned here, but 1 and 2 dimensions is starts with this variational formula. So take an operator whose symmetric part is positive definite. This is so general, one could teach it in introductory functional analysis, and very, very useful. So take an operator whose symmetric part is, okay, negative semi-definite with the minus positive semi-definite. Define its resolvent. There is a very beautiful variational formula for the diagonal matrix elements of the resolvent, which if I take L to be self-adjoint, this boils down to the variational formula for self-adjoint, in the self-adjoint case, which we learn in functional analysis, introductory. This is not very difficult to prove. It's very, very, very useful, I can tell you, and worth knowing for people who do things like that. And okay, if you want a lower bound, choose appropriate test functions, and one can do that from a simple subspace H1 up there in the grading, and it will lead to a variation down to earth, a d-dimensional variational problem, which is tricky in 2 dimensions, but gives the result. And I think that was my last slide, and thank you very much for your attention.
Very much, Bálint, and maybe we have time for just one quick question. Yes, Arnaud?
Yes. So I tell you what it provides.
Yes, and I ask my question after.
In one dimension doesn't make sense. In 2 dimensions, what you expect. In 2 dimensions, I expect super diffusion of order time to the 2/3. But what we can prove, that's a recent paper just appeared in Electronic Communications and Probability with Valco and Ledger. I quoted the paper. We can prove a lower bound similar to, I speak 2 dimension in the Manhattan, a lower bound like this, which is a super diffusive lower bound. In the Manhattan lattice, okay, there is a drop of dimension for some reason, which I don't have time to explain. So in 2 dimensions, it behaves like this guy in 1 dimension. And in 3 dimensions, it behaves like this guy in 2 dimensions. So in this is what we have this in this, okay, recently written down paper. We had the results long ago, just we were lazy to write it down. That in 2 dimensions, we have this lower bound on the diffusivity, this lower bound in 3 dimensions on the diffusivity, and in 4 and more dimensions, applying the central limit theorem for that random walking. So the H-1 condition holds in 4 and more dimensions.
You expect 2/3.
I'm sorry, I don't.
In dimension 2, you expect that the equation are at the power 2/3.
I expect time to the 2/3, the scaling in 2 dimensions. Yes, I'm pretty sure about this. I bet, but I can't prove.
You have ideas of the scaling limit as well? The object.
Ah, that's good. I have no idea what the scale. In 1 dimension, we have the scaling limit in that paper. For this type of anomalous diffusion scaling, we have the scaling limit, the 1-dimensional marginal in my old paper, the construction of the process with Wendelin jointly in that paper in 1D. Absolutely no idea what it should be in 2 dimensions. No, I don't know. It would be a very beautiful thing to make a guess.
Thank you.
Okay, so thank you very much. Bálint, I think we need to...
Thank you.